So, we're going to be talking about matter today, and the first thing we need to do is define what matter is. So, all matter has to have two properties. All matter must have volume and mass. All matter must contain mass and volume. So, we've already talked about the units of volume and the units of mass. So, I want to give you a little bit of a reminder. And the reminder is that milliliters for volume is generally used for liquids, and that's because we can pour them. And centimeters cubed is generally used for solids, and that's because liquids will not make that cube, right? Remember we talked about that we like to use centimeters cubed for solids because liquids will not make the cube. So now what we want to do is we want to take, and this is a little bit of a reminder, a little bit of a review. What if we had a cube that was 1 meter by 1 meter by 1 meter? And we wanted to convert this, so that makes this 1 meter times 1 meter times 1 meter. Oops, I'm making those into I's, sorry. And so the volume of this is equal to 1 times 1 times 1 meter cubed. That's the volume of that 1 meter cubed, right? What if I wanted to convert that into centimeters? So what I would do is I would then convert each side of this, because we're working in volume, that's why I'm doing this now. I would convert each side of this from 1 meters into centimeters. So that would be 10 to the 2 centimeters, 10 to the 2 being 100, 10 times 10. Then I would do it over here, 10 to the 2 centimeters, and I would do it here, 10 to the 2 centimeters. All right? So now if I were to take the volume of this cubed, I would do length times width times height. So that would be 10 centimeters times 10 squared centimeters times 10 squared centimeters times 10 squared centimeters. So ultimately, the volume here would be 10 to the 6th centimeters cubed. 10 squared times 10 squared times 10 squared, and then centimeters times centimeters times centimeters. This should be a little bit of review from that worksheet that we did where you were doing the area, right? So that means that 1 meter cubed is equal to 10 to the 6th centimeters cubed. Are there questions on what I just did? So now, if I wanted to convert a 1 foot by 1 foot by 1 foot, so this one is equal to 1 foot cubed. If I want to convert that into inches, right? So then I would take the same cube, right? And I would do 12 inches by 12 inches by 12 inches, right? Everybody okay? So now I could just set up my box and I could say 1 foot cubed, which is up here, 1 foot by 1 foot, right? By 1 foot cubed. And to convert it into inches cubed, I would say 1 foot cubed is equal to 12 cubed inches cubed. 12 times 12 times 12 inches times inches times inches. How are we doing? Okay? So that's going to give me 1 foot cubed is equal to 1,728 inches cubed. So you can do any kind of conversion here. Simply, you can take any cubic unit and convert it simply by converting the sides into the unit that you want and then multiplying them together. And then you can do that conversion. All right? Okay, so we're going to do a lot of these. I'm just sort of like starting to push you forward in doing these because they're going to become more important as we go. All right, we're at the very beginning stages of that. They're going to become more important. So I'm going to, like, each time I have an opportunity to show you more of these and do a few more of these because they can get kind of complicated, right? So we want to do a little bit more. All right. Okay, and here are your units of mass, grams and kilograms. But what is the difference between mass and weight? And so I'm going to go over this, right? And some of you might feel good about this, and some of you might be seeing this sort of for the first time. So mass is the amount of stuff, and I hate that word, but it's a good word for this discussion. The amount of stuff in a sample. So the amount of stuff in a sample doesn't change here or on the moon. So if I have X amounts of stuff here, if I go to the moon, I still have X amount of stuff. That doesn't change no matter where I am. The amount of particles doesn't change because it's a number of particles. The amount of, you know, if I'm, however you want to count your stuff, the actual number of stuff, and I was thinking about like the number of suitcases I'm carrying doesn't change when I go from here to Alaska. The amount of stuff that I have doesn't change. What does change is the weight of that stuff, and the reason is because the weight takes into account the force of gravity. So the weight factors in the force of gravity. Now, the force of gravity takes into account the mass, in our case, of the planet Earth. And compared with the planet Earth, the moon, the mass of the moon is very small. And so therefore, the gravity of the moon versus the gravity of the Earth is very small. In fact, it's 1/6. The gravity on the moon is 1/6 of the gravity of the Earth. So when we take into account the force that's pulling us, let's say, our bodies down to the Earth versus the force that's pulling our bodies down, our stuff, down to the moon, the force that's pulling it down is 1/6 of the force that's pulling our bodies down to the Earth. So therefore, when we step on the scale on the Earth, our weight will be 6 times the weight that scale will read when we step on the moon. Because the force that is attracting, and I'm going to talk a lot about gravity when we get to air pressure, than the force that's pulling us down into the moon, because gravity is affected by the size, the mass of the two objects that are being pulled together. Now, here's the thing. Gravity is so affected by the size of things and the distance between them that the gravity that we are experiencing here in Florida is greater than the gravity we experience in Denver, which is the mile-high city. Because in Denver, we are a mile farther away from the center of the Earth. What? No. Yeah? Is that true? That is true. The gravity that we experience in Denver is less than we experience here in Florida. Now, it's not enough less that we notice it. We don't notice it. But it is enough less that those tiny little atom particles would notice it. That's the reason that you have trouble breathing. People have trouble breathing in Denver. We're going to talk more about that when we get to air pressure. But at the top of Mount Everest, that is 6 miles from the center of the Earth. So 6 miles from the center of the Earth, those tiny little atoms, they experience a great difference in gravity. Huge difference. Now, if we were running an experiment using those tiny little atoms, that would be a noticeable difference in our experiment if we were using weight, because they weigh a lot less, because they're tiny little, and so the difference in the gravity between here and the top of Mount Everest, or even Denver, is huge to them, all right? And so it's not much to us, but it's huge to them. It's a great percentage of their weight has changed. So that's why we use mass, because the amount of stuff hasn't changed. So scientists use mass, so it doesn't matter whether you're here or you're in Denver working with those atoms or any other particles or stuff. It's all the same, whether it's here or on the moon. Yeah.
You know the fraction of gravity on top of Mount Everest?
The fraction, so that's interesting. I actually could tell you, and you can figure it out. When we get to that air pressure unit, we're going to look at the percentage of air particles that is different between here and there, and so you can actually figure out what the fraction of gravity is. Okay? So we get much more into it. I'm just kind of using that as an example, but when we get there, we're going to actually look much more into what's the difference. All right? Okay, so let's keep going. So your mass on the moon equals your mass on Earth. But your weight on Earth equals 6 times your weight on the moon. So that's a pretty large difference. And it's because the gravity here on Earth is 6 times that on the moon. Okay? All right. So what's next? Well, next we want to look at the state of matter, and we want to look at how mass and volume actually play into it. So for example, solids have a definite volume. Shape, and a definite volume. So what this means is, if I have a solid that's in a container, and I take the container away, that solid will remain in that shape. And it will keep that volume. It will not change. And remember, volume is the amount of space that something takes up. The amount of space that something takes up. So it will keep the shape, and it will also keep the same amount of space that it takes up. Now, liquid does not have a definite shape. But does have a definite volume. So in other words, here, if I have a liter of milk and I take the liter away, the milk will pour all over the floor. But it will only be a liter of milk. It will not spread out to any greater volume than 1 liter. So it won't spread out randomly all over the floor wherever those particles want to go. You won't be cleaning it up and go, hey, there's a tiny little drop way over here, tiny little particles over here. Hey, there's particles way down the hall in Miss Ferg's room. No. That won't happen. It'll stay here. The liquid will stay. And yes, there'll be splatter, but if you added up all the splatters, they would add up to 1 liter. Okay, just 1 liter. Gases have no definite volume, have no definite shape. And they have no definite volume. So what that means is I can have a liter of gas and I can take away the liter and it will have no definite shape. It'll immediately go into whatever shape it wants. It won't stay in the liter shape. But in addition, those particles will go anywhere they want. They will go all over the world. They do not have any attraction to each other. They will not stay together. They will go all over the world. And one of the things that I've been saying today is that's why climate change gases, greenhouse gases, are dangerous to the whole world. Because we as the United States are one of the number one, if not number one, like number two or number three, climate change gas producers in the world. And then what we do is we produce them and they spread out to all these other countries, right? So we can't keep, it's like herding cats, you can't keep your gases into your own country, unlike liquids. If we could produce a whole lot of phosphates and Mexico said, listen, you keep your phosphates to yourself, well then we could say like, okay, like we're gonna have to set up control on our liquid phosphates. We're gonna have to like filter our water as it goes down the Rio Grande into Mexico. I don't know how in the Colorado River, I don't know how we're gonna do it, but we're gonna have to filter that water before it goes in because we can keep control of our liquids. But what we can't do is we can't keep control of our gases. Now, one of the interesting thing about it is that one of the highest producing greenhouse gases is what? Cows farting. This is one of the biggest problems, especially that Americans have, is that we eat so much meat and cows produce methane when they burp and fart, and we consume so much red beef, like beef, that we're one of the highest beef consuming countries in the world, and we eat so much red meat that our cows produce something like 18%. Mr. Wood just looked it up, and it said 18% of the methane in the world. 18%. And methane is the worst greenhouse gas because it's the warmest it keeps the warmest amount of temperature, like the highest amount of temperature methane does. The reason that people don't talk about it is because it's not one of the number one greenhouse gases produced. But cows, it's the worst greenhouse gas, and cows produce 18% of it, burping and farting, and we eat the most meat. So what they say is if you would just have 2 meatless days a week, as in all vegetables and grains, you would drastically help to reduce greenhouse gases by having 2 meatless days a week, because meat producers would have to stop producing so much meat, and therefore fewer cows, and therefore less methane, which is one of the most dangerous. Sorry. All right. Yes.
If cows go away, we'll just find another animal to eat.
It's not that we eat them. It's that what they eat that produces the gas.
Grass.
It's grass and grain, right? Okay, so the other thing is plasma, number 4. So 1, 2, 3, 4. The 4th state of matter is plasma. Plasma is matter that has energy so high that we cannot contain it on Earth. The example is the sun. In other words, this is not a state of matter that is contained in your plasma television. That is a commercialized term that is used by, Toshiba and Samsung. That is not real plasma, scientific plasma that is contained in your TV. It's just like, it's just a word that they are using to make it sound interesting so you'll buy it. Plasma, it can't be contained on Earth because the heat and energy in it is like the sun. So that's not in your TV. All right? Okay, we're going to stop here. Okay, you have everything you need for tomorrow. All right?